Greetings, first of all. I hope everyone is doing well and is fit and fine by God's grace during these challenging times, and my best wishes and prayers for you and for your family. In this video, we're going to discuss about the stationary points and the tools how we can identify the stationary points and discuss their nature graphically with the help of technology as well as manually, and what are the required methods. First of all, let's look at the first derivative test. What's the first derivative test? First stationary points. If we have any curve y is equal to fx, and we find the gradient at x is equal to a, and then f of a is the local maximum if the gradient changes sign from negative to positive at x is equal to a, as shown in the sign diagram on the screen. Second point, the point a, f of a is the local minimum if the gradient changes sign from positive to negative at the point x is equal to a, as shown on the right hand side. So gradient at the left side is positive, at the right side is negative. Double derivative test. So if at x is equal to a, first derivative is 0 and double derivative is negative at that point, then we call that point is a maximum, and if the double derivative is positive at that point, we call that point as a local minimum. Now what is the concavity of the curves? Let us say we have any curve y is equal to fx at an interval I. If double derivative is 0 and have an inflection point where a is any value of x, then the curve is said to be concave up for all the values in the interval if double derivative is greater than or equal to 0 at that point. And if the double derivative is negative at that point, then we call that curve as concave down. Stationary point of inflection is also known as horizontal point of inflection. If first derivative is 0, double derivative is 0 at that point, and double derivative changes sign at that point, as shown in the sign diagram. At the left side of a, double derivative is positive, on the right side double derivative is negative. Then we call that a horizontal point of inflection. What's non-stationary point of inflection? These are just basic definitions. First derivative is non-zero, but double derivative is 0 and double derivative changes sign at that point, like shown with this help of sign diagram. Now what if the first derivative and double derivative both are 0 at a point and double derivative doesn't change the sign? Then no point of inflection exists, but that point may have local maximum or minimum value at that point. So we confirm by first derivative test. So double derivative does not change sign at that point, and double derivative is 0, first derivative is 0. Now for example, let's say x raised to power 4 and negative x raised to power 4. The graphs are shown also. Let's first find the derivative of x raised to power 4, that is 4x cubed. And then double derivative 12x square. First derivative and double derivative both are 0 and double derivative is positive for all x. So we confirm that 0, 0 is the local minimum because double derivative does not change sign at x is equal to 0. Similarly, for y is equal to negative x raised to power 4, the red curve. First derivative negative 4x cubed, double derivative negative 12x square, first derivative, second derivative both 0, double derivative negative, and does not change sign for all the values of x, so therefore local maximum. So let's consider a very interesting example, 2x raised to power 4 minus 4x square plus 1. Find all the turning points and determine their nature. What are the intervals where it's increasing or decreasing, and find the intervals where the graph of f is concave up and concave down, and sketch the graph of f indicating any maximum, minimum, and points of inflection. Solution. First of all, write the curve as it is, find the gradient, equate first stationary points, equate the gradient to 0, and factorize x is equal to 0 and x is equal to plus or minus 1 are the two points where the first derivative is 0. Then again differentiate the first one and find the double derivative. So when x is equal to 0, double derivative is negative. When x is equal to 0, double derivative is negative. So therefore it's a maximum point. When x is equal to 1, double derivative at x is equal to 1 is positive. So therefore x is equal to 1 gives us the minimum point 1 comma negative 1. And when x is equal to negative 1, double derivative is again positive. Therefore x is equal to negative 1 gives us the local minimum point, that is negative 1, negative 1. Now therefore the points 0, 1, 1, negative 1, negative 1, negative 1 are the turning points of the curve. B part. Since gradient first derivative is negative for x less than or equal to negative 1 and 0 to 1, and therefore fx is decreasing for negative infinity to negative 1, union 0 to 1. We can see in this sign diagram for the first derivative, because for increasing and decreasing curve, sign diagram is very helpful. On the left side of negative 1, we can see the negative gradient, and therefore from 0 to 1 also the gradient is negative. So therefore on these two parts the curve is decreasing. Since gradient is positive for negative 1 to 0 and x greater than or equal to 1, so we can see the f is increasing for these two intervals. For concavity, we need to check the sign of the double derivative or the gradient of the gradient function. So we equate that to 0 to find the endpoints. So therefore we have x is equal to plus or minus 1 by root 3. So we'll check with the help of sign diagram. Let's see the sign of the double derivative at x is equal to plus or minus 1 by root 3. Now we can see at negative 1 by root 3 on the left side derivative is positive, on the right side is negative. Means double derivative changes sign at x is equal to negative 1 by root 3. Similarly it changes sign at x is equal to 1 by root 3. So since double derivative is positive for x less than negative 1 by root 3 and x greater than 1 by root 3, therefore we can say curve is concave up for these two intervals. And since double derivative is negative for negative 1 by root 3 to 1 by root 3, so therefore curve is concave down for this interval. Again we can see that double derivative is 0 at this point negative 1 by root 3 and changes sign. First derivative is non-zero at both points. So therefore we can say that x is equal to negative 1 by root 3 and 1 by root 3 are the non-stationary points of inflection. Let's see the graph with the help of technology. This graph is drawn with the help of Geogebra. So we can see from this graph the points H and I are the non-stationary points of inflection, and points A and point C local minimums, point B is the local maximum. Let's verify with the help of graphics display calculator as well. For stationary points found in the previous part, with the help of graphics display calculator for the curve y is equal to x raised to power 2x raised to power 4 to x raised to power 4, then minus 4x squared minus 4x squared plus 1, and then go to the window, adjust the window. This the window is here, so we can adjust the window. Let's say negative 5 to 5, so we can say negative 5 x minimum, maximum 5. We can readjust if we don't get the clear picture on the screen. And negative 5 to 5, so that yeah, so we have a W type shape. W means wall but we can see whether it matches with our points or not. So we have two minimums, one maximum, local maximum, two local minimums, and two non-stationary points of inflections also. So let's see, if you want to see local minimums, number 3, press number 3, and bring the cursor near the minimum point, enter the left bound, and then cross, enter the, so we have minimum point as approximately -1, that is -1, and that is correct. For the second point of minimum, take the cursor near the point, the left bound, and we have again 1 and -1 as our local minimum. For maximum, we can cross check. Sometimes paper 2 question, so GDC can be very helpful. We should enter the parameters very carefully. We should press the left and right bounds very carefully. Left bound, then right bound, and then so x equals 0, 1 is the maximum, local maximum.